So let's imagine that we have a ball on a track that at the bottom of that track, there is a block. And the ball is going to be, this is a frictionless track. We'll say that our track is 1.5 meters high, or 1.2, because I wrote a 2 instead of a 5. 1.2 meters high. The ball has a mass of, let's say 2 kilograms. Watch me make a bad problem on the fly. The block has a mass equal to 1.5 kilograms. And it's got a sticky pod here. This is sticky. So that they're going to collide and stick together. Okay? So the question is, how fast will the block be moving? So there we go. We'll answer that question. All right. So we are going to be able to use this to look at both conservation of energy and conservation of energy. So we're interested in how fast the block is moving. And like you've heard me say over and over again, let's start with that. Start with what we're interested in, and physics will guide us to what we would need to know. So we're going to start with the block. And we need to recognize that this is a collision. It says collide, so that helps us a little bit. But this is an interaction between this ball and the block at the point of contact that's going to influence the motion of the block through the system. So in thinking of a collision, we know that momentum has to be conserved. So that tells us that the initial momentum of the system has to equal the final momentum of the system. So what's the system? Remember, in momentum conservation and in energy conservation, we have to think of the system. What is the system? Well, the system at this point is the ball, because remember, it's going to come down and stick, and the block. The ball and the block is our system. So our initial is right before the collision. Our final is right after the collision. So right before the collision, we have the mass of the ball, the initial velocity of the ball. We have the mass of the block and the initial velocity of the block. The mass of the ball, we're told, is 2 kilograms. The ball is moving, but we don't know how much. So we don't know this value yet, but we know it has one, so it's going to have a value. And we know that at this point, it'll be moving to the right. So we're going to identify that as positive. The mass of the block is 1.5 kilograms. And the initial velocity of the block is 0. We don't know the initial, or we do know it. It's not moving. It's just hanging out there at the bottom of the track. In the final case, our masses haven't changed. So the mass of the ball is 2 kilograms. We don't know the final velocity of the ball. That's what we're interested in because they're sticking together, so the block and the ball will have the same final velocity. Mass of the block is 1.5 kilograms. The final velocity of the block, we also don't know. But again, these two are going to be the same. So we'll just call them the final. All right, so let's proceed with our system. This then, the initial momentum of the system is the initial momentum of the ball plus the initial momentum of the block. That has to equal the final momentum of the ball plus the final momentum of the block. I guess I called it should be consistent. The initial momentum of the ball is the mass of the ball times the initial velocity of the ball plus the mass of the block times the initial velocity of the block, which we know to be 0. So that's going to go away. That equals the mass of the ball times the final velocity, which we've down defined as v final, plus the mass of the block, oops, that's an E, times v final. All right, so we know some of these values. We know the mass of the block is 2, but we don't know the initial velocity, sorry, the ball. We don't know the initial velocity of the ball. We have 2 v final plus 1.5 v final. So we can do a little bit of combination of terms. So 2 times the initial velocity of the ball is equal to 3.5 times the final velocity. So I just factored out the v final and combined the 2 and the 1.5. So in order to solve the conservation of momentum problem, this is the process we do that. We need the initial velocity of the ball. If we had that, we'd be golden and could solve the problem. So let's now practice conservation of energy to get that value. Conservation of energy, I'll do that in blue, tells us that the total energy at the beginning, whatever we define as the beginning, is the total energy at the end. Now, the beginning and the end is our choice based on what we're trying to solve. But energy doesn't change throughout, so it could be any 2 time points within a situation. So what's the situation where energy is involved? Well, the ball has a certain amount of energy, potential energy. It's related to its position, and so it's high. It has some gravitational potential energy. And we know by energy transformation ideas that and conservation of energy conceptual ideas, that as the ball travels down, it loses potential energy because the height goes down, and it increases its speed because it's gaining kinetic energy as the energy transformation goes from potential to kinetic. So at the bottom, it is going to have more kinetic energy and less potential energy. Now, how much potential energy we have depends on where we set our reference height, so we want to be strategic about that. And that means we want to be able to maybe get rid of some potential energy because we set height equal to 0 at a certain position. So often we will set that height sort of where we visualize the lowest level of the activity of the object we're interested in. So we're going to put a height equal to 0 at the bottom. Then it doesn't have any potential energy at the end because it's at height 0. It's all kinetic. All right. If this ball is dropped at rest, from rest, then we don't have any kinetic energy at the top. That makes life easy to solve and is strategic in our process. So the total initial energy is the total gravitational potential energy plus the total initial kinetic energy. That equals the final gravitational potential energy plus the final kinetic energy. And as a reminder, this is also potential energy initial. You'll see it this way as well. And this is actually how it shows up on your equation sheet, because I think it's a little more intuitive for you. So potential energy initial, kinetic energy. Whoops. Gotta hit a massive initial. All right. So potential energy is the mass times gravity times the initial height plus 1/2 mass times the initial velocity squared. So we're also practicing those equations right now. Final potential energy is mass times gravity times the final height plus 1/2 mass times the final squared. Now, why am I interested in this? Well, the final of that ball is the speed at which it hits the block. So that's why we could use energy to help us solve our momentum problem. All right, so we have the mass of the ball, 2 times 9.8 times the height of 1.2. It's not moving, so this whole term goes to 0. At the end, we're at height 0, so that whole term goes to 0, and we're left with 1/2 m. Oops, that's 2 times v final squared. So 2 times 9.8 times 1.2 divided by a half, divided by 2, which is really just nothing. And then we take the square root of that, and we get a velocity final of 4.85 meters per second. So here is our example of conservation of energy, kinetic energy, and potential energy recap of equations. So now we can use that in our momentum equation and finish up our conservation of momentum problem. So we have 2 times 4.85 is equal to 3.5 V final. So times 2 divided by 3.5, and we get V final is equal to 2.77 meters per second. Now, does that make sense? Well, it's less than the ball was at the beginning, which should happen since now these two objects are together and collide together. All right. So I guess we hit